This podcast is brought to you by LMU Munich.
Hello everybody, good morning. So this will be a Blackboard talk. I'm sure that many of you have heard that there are issues with unifying quantum mechanics with gravity. What I will discuss in this series of lectures are specific issues associated with black holes that are special states in gravity. And I will mostly use the standard tool that people use in this subject, which is quantum field in curved space-time. This is analogous to n equals infinity in ADS-CFT. And what we will see is that when we try to apply the simplest principles of general relativity, the equivalence principle, and we combine it with the simplest principles of quantum mechanics, in particular unitarity, we try to put these two together in the context of black holes, and we get an immediate contradiction. And so from then we have to decide what to do, because we know that general relativity is correct. This has been checked experimentally and also it's consistent. We know also that quantum mechanics is correct. So it's very hard to change any of them. And in fact, I would claim that you don't need to, that most of the issues that are associated, or the main issues that are associated with this clash are related to treating black holes as too classical. We have to treat them as quantum mechanical objects. And what I will try to do in these lectures is, first of all, so the plan would be am I writing big enough so that the last rows can see? And here, what we will see is that if we consider gravitational collapse, and we apply the standard rules that we are instructed to use for matter fields in this background, we find that unitarity is broken. So that's essentially taking the point of view of general relativity, letting it be the guiding principle, geometry, general relativity, and then we find that unitarity is broken. Then the second part we switch a point of view and we say what we basically, I think by now everybody agrees, almost everybody, that we cannot break unitarity. We cannot just say that unitarity or quantum mechanics is incorrect because there's too much evidence that it is. So now we switch point of view and we say, okay, let's insist that unitarity is preserved, and let's see what are the consequences? And here, here we will discuss the page model, which in a way is the simplest model that actually implements this idea. This page is a person, is Don Page, and this is a model from '93. This is based on the paper of Hawking from 1976. So you see, these have been around for a while. And then the so-called firewall problem, which in a way is an attempt to combine the Hawking model or put more ingredient from the Hawking model of gravitational collapse in this context. Okay, and then this actually will show us that if we insist that, then essentially we find we follow this idea, and we find that the equivalence principle is violated. So going from this way and going from that way, there doesn't seem to be a way to put these two principles together. And as I said, that I believe that an important ingredient in resolving this issue is treating black hole as quantum state. So in the last part, I will explain how to treat black holes as quantum state. And see what the consequences to these two points of view are. Now, you see that I listed here 3 subjects, and I will I will have 4 lectures, so the partition will not be exactly, each lecture will cover a subject, but there will be some overlap. I prepared some problems for the students, which you are encouraged to work. And as I told the organizers, I'm willing to stay after the lectures to explain the problems, and then the next time, if necessary, to discuss the solutions. And since you know well that you cannot learn without doing actual problems. So I encourage you to take advantage of this opportunity. And even if you can't solve the problems completely, at least try to think about them or try to start solving them so that it will be easier for you to follow the lectures. Also, you're welcome to ask questions during the lecture. The worst that can happen is that I will tell you that I will either answer it later or answer it in private. But the idea is to try and make it similar to a class, at least a class in Israel, where people are usually can ask questions and it's okay. Good. So let's start. Okay, so we start with the information paradox. And I will start with some preliminaries. I believe that most of you have seen part of, at least part, if not all of what I'm going to show now, but I have to just lay it down so that we have a concrete way of discussing. So let me remind you about the Schwarzschild geometry in 4 dimensions. This is we will only do 4D. The generalization to higher dimensions is easy. So this. The Schwarzschild radius is 2gm. I suppress for the moment h bars and c's. Well, here there's no h bar, but I will also be using advanced time and retarded time, and R star is the tortoise coordinates. Yes. To m ln of r over 2m minus 1. Okay, and now, so this is the Schwarzschild geometry, and we will be interested in a geometry of a collapsing body. Okay, and what we will discuss in particular is a geometry of a collapsing shell of matter. Okay? And so, in this case, we draw a Penrose diagram. So as you will see, the first problem is to actually draw a Penrose diagram on the computer. I hope that many of you know how to use Mathematica or MATLAB or some other programs to create graphs. And so this would be, actually, if you haven't done it before, it's a very interesting exercise, because it makes Penrose diagrams into something that you can actually feel with your hands. Okay? So I think I need a bigger one, but let me start. No, bigger one. So this is the horizon. This is called scribe minus, and this is called scribe plus. I will not go into the details of that because I assume that many of you have seen that. And if you haven't, you will do the problem and refresh your memory. So this is the surface of the shell. And now, and this is the center of the shell, and this is also r equal to 0. So you see the shell collapses and reaches 0 size. And now we are interested, you see, let's look now here about the trajectory of light rays that come from infinity, go through the shell, and then escape to infinity, okay? Now, there are two kinds of trajectories. One trajectory goes through the shell and actually escapes to infinity. And another kind of trajectory enters the shell, and because the shell has already collapsed inside its Schwarzschild radius, it cannot escape to infinity. And in terms of this advanced time v, we can see that here v's are 45-degree line. So v0 is the last time that a shell can escape to infinity, that a light ray can escape to infinity. Here is a light ray for v less than v0. And here is the light ray for v larger than v0. Okay, questions so far? Good. We will be, in this discussion, interested in light rays that can just escape to infinity. So they're escaping from the shell just before the horizon is formed. This is what will be our point. Okay. Now, we do quantum fields in this background. Okay? So we now discuss, rather than classical light rays or classical projections of particles, we discuss quantum fields in this background of the collapsing shell. I should write here problem 1. Draw. So not a shell, so the problem says draw a Penrose diagram of a collapsing star, not a shell. Okay, so the difference between a star and a shell is that the shell is empty and the star is filled with some matter. So you decide what type of matter you want the star to be filled with, and then draw the Penrose diagram of the collapsing star. It will be similar to the one that I drew, but you will find out. Okay, so now we do quantum fields on this background. And what we do is we set up So, yeah. So we have to sorry, I minus. So we have to, in this case, to define the expansion in annihilation, creation and annihilation operators. We have to define positive frequencies, and we have to put boundary conditions. And so in this case, f goes like e to the I omega v. So again, if I now again draw the Penrose diagram, here I have the F's are essentially ingoing waves that come from infinity. And I can also define the ingoing vacuum, 0 minus which is essentially annihilated by all the annihilation operators. So this is completely standard quantum field theory. Again, I assume that this is something that you are familiar with. Now, this construction is almost well defined. It's almost well defined because this is curved space. And the distinction between positive and negative frequencies is not quite exact as it is in flat space. We will discuss it later. Okay? But we will encounter cases where the construction is much less well defined than in this case. Now, so this is I minus. And this is I plus. Now, we will be interested in observing what comes out of the shell. Okay? So, in this case, we have to change bases so that it fits our desired goal. And the way we do it is we go to another basis. So we write, in this case, phi, which is sum I pi bi plus pi star bi dagger plus qi ci plus qi star ci dagger. Okay? And in this case, the boundary conditions that we put on the B's and the Q's are different. So the pi are defined by only positive frequencies at I plus. So they are purely outgoing. So they go as e to the I omega u. And they have 0 Cauchy data on H plus. So the P's are outgoing waves at infinity. Okay? The F's are incoming waves from infinity, and the P's are outgoing waves from infinity. But this is not enough. We also need the Q's, and they have no outgoing component. Now, this definition is actually not quite well defined because it's very hard to define positive frequencies for the Qs. So I cannot really separate positive and negative frequencies here. Right? This feature will be important later on because this type of picture is the basis of the pair production picture of Hawking. So you should remember that. But luckily, since we are interested in observables at infinity, and the Qs have no outgoing component, the observables at infinity, at plus infinity, will not depend on the choice of Q. Only the state near the horizon will depend on what the Qs are. But what comes out at infinity will not depend on the choice of Qs. So these ambiguities will not affect what we see at infinity. Okay? Clear? Questions? Good. Oh, yes? I did, right? When I initially I defined the basis for the whole space by setting it up, setting boundary conditions at minus infinity where space is flat, and so I can do everything almost perfectly. But this is an inconvenient basis if I want to find out what happens at infinity. Because I need, as you will see, I need to find a transformation from the ingoing to the outgoing and find out what comes out, the spectrum and the properties. So I have to go to a basis where this can be done in an easy way. Did I answer your question? Yes. No, in this case, you can do it. Right? So again, I'm not entering to this type of details, but the paper of Hawking from the PRD 76 paper of Hawking, which I recommend, is really a remarkable paper, and he actually explains that very clearly. And in fact, there is a paper of Ford, which I will soon mention, a review paper which does that even more explicitly. So these issues, again, you should actually check for yourself when you're solving the next problem. Okay, more questions?
Where is the observer? Where is the observer? I mean,
In this case, for the moment, there are no observers. You are setting boundary conditions, and what we are interested eventually is looking at expectation values, so observers that observe what comes out at plus infinity. Okay? But for the moment, no observers. Good. So we continue. Now the outgoing vacuum zero plus is defined such that all these annihilation operators annihilate it. It's a different state from the zero minus. Now, because F is complete, then I can express the PIs in terms of the Fs. And the BIs in terms of the A's as a linear combination these are called Bogoliubov coefficients. These are called Bogoliubov coefficients. Now, let's now think about what we found. So in this case, the betas generically will not be zero, right? They will not vanish. Okay? So what does it mean? What does it mean in terms of what an observer at infinity will see? It's true, but you can speak up since you are saying correct. Your answer is correct. So, what's your name? Rosia? More or less. She said that if the betas are non-vanishing, then this means that the state at infinity contains some particles if viewed by someone who defines particles at minus infinity, right? So Hawking interpreted this phenomenon as saying that this collapsing shell is emitting particle. Essentially, it's burning an emitting particle which reach infinity. And our task now is to compute this flux of particles that the shell is emitting. But before that, let me give you a preview, a trailer of the result. What he found is that the state of the outgoing particles is a mixed state. The density matrix is diagonal. I will explain these terms if some of you don't know what it means. But in this case, if it's true, then this means that we started from a pure state, 0 minus times the shell, and we ended up with a mixed state. Now, unitarity, quantum mechanics says that this is impossible because unitary evolution takes pure state only to pure state. Of course, in this case, we could have started not necessarily with a pure state, we could have started with a mixed state, but what this phenomenon will say is that the purity of the state decreases. These are terms that I will explain, and therefore this phenomenon is incompatible with the principles of quantum mechanics with unitarity. Even though we are only using quantum mechanics here, as we were instructed, nothing seems to be a problem. Okay, so now most of the calculations leading to this you will do as a problem, but let me explain to you the idea of how to calculate and also give you an outline of the calculation, and then I will also give the results. Okay? So the main effect of the main effect that is causing this particle production, this emission of particle by the shell, is the large phase shift that the large phase shift that a mode that is entering the shell and exiting just as it's about to create a horizon, that's really the main effect. And as you can see, so let me draw it like that. And then, right? So the shell is collapsing, and now I'm finding a relationship between an incoming mode and an outgoing mode. So when the incoming mode is entering the shell while it's still away from its Schwarzschild radius, and exiting much closer, when it's much closer to the Schwarzschild radius, you see that the V and U variables are very large. So the phases of the modes, the modes oscillate very quickly, and you get a large phase shift when transforming both of them. And the idea of the calculation is to calculate this phase shift, and from that find the Bukolivo coefficients. And so in this case, let me write it here. So and because the waves oscillate very quickly, we can use geometric optics to trace the rays, and this way calculate the coefficients. Okay, so let me now give you problem 2. So is a calculate for a thin shell. This was done, well, it was done by Hawking, but a very nice review and detailed reference for the calculation is this paper. And again, we do that. So A, show that U okay. So again, you should use ray tracing and connect the different coordinates as they go through the shell. And we are interested in V's that are close to V0. Okay, then we should show that P omega is e to the minus 4m I omega log V0 minus V over C for V less than V0 and 0 for V larger than V0. And then C so I now switch from the finite wave function basis to Fourier space. Can you see upstairs? Is it still visible? Okay, so for that, show that beta omega prime omega is equal to T omega. That's a transfer coefficient. You should forget about it. So you basically need to do this integral with the p that you found before and get this result. And there will be also an overall phase factor, but that I forget. And TW is a transmission coefficient, which again is I will not discuss. Okay, so now I'm any questions about the problem? No, good. So now I'm assuming the results of the problem. And what I would like to find out is the spectrum of the emitted particles. Okay? So how many particles are emitted at which frequency? Is this what I would like to do clear? Good. So what do I need to do? I need to calculate the expectation value of the number of particles, right? This is how I find the spectrum of the emitted particles. So I have to compute additional quantities, but this is the simplest quantity that I can compute. You agree that this is what I should compute? No? Yes? I have to find out, as we agreed before, the fact that the coefficients betas are not zero means that the outgoing state contains particles. So if I wish to know how many, I have to compute the expectation value of the number operator. And this is what I do. And in this case, when I go to the continuum normalization, I do it using my beta omega, integral from 0 to infinity d omega prime, beta omega prime omega, beta star omega prime omega tilde. Okay, so this is the expectation value of the number of particles. And now I can, since I have the result of the problem, I can compute it. So, what is it? These are just factors of normalization that do not depend on omega prime. And then there is the two gammas. And then the important integral, 0 to infinity, d omega prime. So you see, it's only these factors that come in. So it's omega prime to the minus 1 plus I for m omega minus omega tilde. And so can you guess what is the result of this integral? It's actually a very simple integral. So let me show you. So what I do is I define y to be lambda omega prime, because you see here there is d omega prime over omega prime. And then this becomes integral from 0 to infinity d omega prime, dy, from minus infinity to infinity dy, e to the I y for m omega minus omega tilde. Now this integral you should recognize. Do you? Okay, it's a delta function, right? So what have we found? First of all, we have found that there is some amount of particles are produced. When we plug in this delta function here, things get very simple. And in fact, using this result, we find that the production is actually a thermal production, and your problem 3 is to actually show that. So calculate n omega and show that the temperature is 1 over 8 pi. But the most important aspect here is that there are no cross terms. So there are no terms that are of the form b I dagger b j, where I is different than j. Okay? Only diagonal terms. And this is the first indication that that we see that the density matrix, the state of the outgoing radiation, is diagonal. If the state is diagonal, it is mixed. The density matrix of a state corresponding to a state is diagonal. The state is mixed. And so we go back to my previous comments, but now we are one step closer to establishing this result. And notice that we have only used standard techniques, calculations. There doesn't seem to be any loophole in going through this. And once you actually do the calculation, you will see that it's a straightforward calculation. Good. Questions so far? No, everything is clear. Very good. So now, I think I can erase this, but I probably need the whole blackboard. Okay. I use the non-German way. This is something that I wish I knew, but the other one. So now what we would like to do is essentially progress towards establishing the fact that the density matrix of the outgoing radiation is diagonal. So the state is mixed. Okay, so Hawking actually claims that, so the density matrix or proves it. Now, the way I'm presenting it here will be valid only for free field. You remember we were discussing scalar field as models for quantum fields. And in this case, I will only consider free fields. So, but so it's valid for free fields. And actually, what he claims is that the density matrix is thermal. So a thermal state. So there's a quick and dirty way of proving it, and the quick and dirty, which Hawking doesn't do. Because these are free fields, So free fields. It means that the density matrix is Gaussian. For some matrix Mij. Okay. But we have calculated, we have seen that this was proportional to delta Ij, right? This is the calculation that we did before. So this means that Mij is diagonal. Now, the best way to prove the fact that the density matrix is diagonal is use path integral methods. So such as Gibbons Hawking and so on, there you can actually, using the path integral, you can actually calculate the density matrix and show what the matrix Mij is and show that it is diagonal. We will not do it here, but I will, in the notes that I will upload to the web, there will be some references on how to do that. The weakness of these path integral methods is that they need eternal black hole space-time. So they cannot be used in a straightforward way to a situation where we have gravitational collapse. And as I said, in this case, well, I'm not sure I said it. I said that we should treat the black hole as a quantum object, but the eternal black hole actually is infinite has infinite mass and doesn't fluctuate. So using these methods is much harder if you wish to understand the fate of a physical black hole. And that's part of the reason that I'm not showing this. Okay, so let's see how Hawking proceeds in the proof. Recall that we expanded our scalar field in the Q and P bases like so. You remember the modes, the outgoing modes and the modes that go, the ingoing modes. Okay, so we can write the incoming vacuum as some general superposition of outgoing modes and ingoing modes. And in this case, A out is this the standard defined in the standard way. Whatever that means. As I said, this is not quite well defined, but luckily this definition will not affect what comes out at infinity, and NJA and KB are particle numbers for a specific mode. And these are configuration index. Configuration indices. Now, we have to write the density matrix for the outgoing state. So, as I said, it's something that is not quite well defined. I can define it in words, right? I can say this is a state where near the horizon there are no particles. But that definition is not that doesn't, for example, if you wanted to translate it into equations, it would be a problem because of the problem that we discussed before of separating the positive and negative frequencies, defining particles, etc., etc. But because we will eventually be interested only in what comes out at infinity, and the result will not depend on the ingoing modes, the Q's, then we can swing it by. When we discuss the pair production, that becomes a bigger problem. And in fact, one of the caveats that I will mention about the pair production picture is that it should only be heuristic. So in this case, you have to differentiate between what you can actually calculate precisely and the associated words that come with the calculation. So this is part of the associated words. So now I would like to calculate rho out, which is trace over the in mode of the full row, which is basically trace over the in mode of 0 minus 0 minus. So in this case, rho out A C is equal to sum over B, lambda A B, lambda star CB. Okay? So this is the density matrix. And the plan of the proof is show that rho out is proportional to, so rho out of is proportional to a delta function which means, so let me explain what that means. You remember that we did the calculation of the number operator, or the two-point function, and we found that it vanishes unless the particle kinds, the frequencies match. Okay? And also the number of B's and number of B-daggers have to match. So now the claim here is that the density matrix, or these expectation values, this type of expectation values vanish unless the number of particles, unless it's just a B dagger B to some power. So if there's a mismatch, if there are different frequencies, or the number of particles in different frequencies don't match, then the density matrix elements vanish. Is this clear? Good. So, and again, this will be a subject of a problem. In fact, as far as I know, there isn't in the literature, I couldn't find in the literature a complete proof of that. So you have an opportunity to complete that proof. And I will try to outline a problem that will allow you to do that. So the first point is that rho C can be completely determined by expectation values of the form 0 minus B I to the M, Bj dagger to the N, 0 minus. And as you can see explicitly here that this type of expectation values, the girl who asked before, you see that these type of expectation values do not depend on the Q, because the B's and the betas only are associated with the P's. Because they never go out. And we are looking at what comes out.
Like it's part of the physics. It's part of the,
Yes. So the idea in this case is to look at what comes out. So it's like a scattering experiment. You're creating a bound state, and you look at what comes out. And eventually everything comes out. So you're collecting everything, and you should have all the information.
but obviously not everything is coming out.
All the energy, all the particles, all the charge eventually comes out in this type of model, right? Because there's a constant flux. The shell emits particles. By energy conservation, its mass decreases. And eventually, so what this shows is not that everything doesn't come out, but it comes out in a way that is incompatible with the principles of quantum mechanics. And you will see in the later talks that you don't have to wait until the black hole completely evaporates. You already see signs for problems with unitarity when the black hole is about half its size. So when it's still big, and if you're sophisticated enough, you already see that there is a problem there. So the conclusion is not that not everything comes out, it's that there is something that we are doing wrong in this treatment. But when you go and do it step by step, there's nothing that you can point your finger to. And in fact, with the assumptions that Hawking made, it's a correct conclusion. That's the information paradox. Okay. So, for example, now this I think should be reasonably clear, right? Because every operator I can expand in polynomials of creation and annihilation operators, so I can essentially find every matrix element of rho if I knew all the matrix elements, all the expectation values of this form. So in this case, for example, this expectation value vanishes. This we can almost immediately see because because you see that the B is a linear combination of A and A dagger, just n to the first power. So if I take an expectation value in 0 minus of this operator, it vanishes, right? And similarly, as you will see in problem 4, this expectation value bi to the m bj dagger to the n 0 minus is proportional to delta ij delta mn. Okay, so now before there should be a 50% probability that I push the correct button, but I seem to be pushing the incorrect button 100% of the time. So before I go to writing down problem 4, is that you see from here is that, you don't. You see already an indication in problem 4, if you can do it, will show that it works continuously. You see that if the M and the M don't match, and then if the I and the J don't match, you get 0. So the only non-vanishing possibility is if the I and J match and M and N match. Okay? So this is, if you wish, another indication that the density matrix is diagonal. You can only have this type of matrix elements. And in fact, by looking at expectation values of this form, you can show that the density matrix is not only diagonal, but thermal. So what we started with here. But the thermality is not that important. The important fact is that the density matrix is diagonal and has more than one non-vanishing eigenvalue, so it's a mixed state. So what do we get? We get that we started from an initial state which we could take as close to pure as we could, because we start with essentially 0 minus shell, a collapsing shell of matter times a vacuum, incoming vacuum for the fields. And this goes to a final state that is rho, thermal density matrix. So what we conclude from here, or we should conclude, that the time evolution is not unitary. Because under unitary time evolution, the pure state should go into pure state. The purity cannot change. And the result doesn't depend on our assumptions on the ingoing modes Q's. So we have a problem. Now, what Hawking goes on in further says, well, like everybody else, I'm sure that you were thinking there must be corrections to this result. And what he argues, that corrections are exponential in the black hole entropy, area over Planck square, area in units of L Planck, area in units of L Planck. And so in this case, if these corrections are so small, they cannot affect that. And the way he argues about that is by showing that by how much the definition of positive and negative frequencies is affected by the fact that this space is curved. So this is the almost well-defined that I talked about initially. There is some ambiguity that is essentially proportional to the curvature, energy proportional to the curvature. So this means that the frequency is not well-defined up to the scale of the curvature, and from that you get this type of correction. This actually turns out to be incorrect, as I will show you explicitly. Well, what he said is correct, but there are larger corrections that go like 1 over SBH, so that's LP squared over RS squared, and are not exponential. Okay, so I just have time to write down question 4, problem 4. So let me do it. Let me do it here. Technical problem. It's okay. So problem 4 is essentially go through the steps leading to the conclusion that the density matrix is diagonal. So A show that show that it vanishes for I different from J. B, show that E is completely determined by waves of polynomials of BI and BJ Dagger. C, show that the density matrix is diagonal in total number of particles so N is some Ni. So this is a slightly simpler problem than actually showing that the full density matrix is diagonal. Just need to look at configurations that have different total number of particles, and then show that the expectation values of the corresponding operators vanish. And then D, show that rho out is diagonal in the and as I said, as far as I know, D doesn't exist in the literature, so you have an opportunity to complete the literature. I'm not sure if it's worth a paper, but at least a chapter in a master thesis. Okay, I'm done. Thank you very much.
Do you have more questions?
Yes.
Quantum mechanics, one has non-unitary time development in the case that the measurement takes place.
In the case of?
That the measurement was made on some system. The measurement splits up the matrix into the diagonal ones.
The measurement projects the density matrix. Yes, but here this issue is of projecting or measuring is not has not yet come into play. This will come in the next time when I insist on unitarity, and I will describe. Here, I just followed the rules of quantum mechanics, and I computed the expectation values of outgoing particles, essentially. How many of them?
We looked at as if a black hole acted like a measurement device. So it comes out.
Well, yes, but the point here is that eventually the black hole, so you should think about it this way. The shell is collapsing, so you should think about it as a scattering process. A resonance is created and it decays. And I wait until it completely decays, and then I look at what comes out. Okay, so I do the measurements, if you wish, only after the black hole or the resonance has completely disappeared. Or as I said, I can wait until it's half disappeared and I will see the same probe. So in this case, the issues are not associated with incorrect implementation, as far as I know, incorrect implementation of the rules of quantum mechanics or incorrect interpretations according to quantum mechanics of the result. This, right, so it's not, that's, as far as I know, that's not where the problem is. Okay, additional questions?